from class. You got a M1 is hanging there, M2 is on the top of the table, and M3 is on the ramp. I call the left tension T1, the right tension T2. You have some F2 that is pushing M1 into the ramp, which will cause a normal force, which then will cause friction. And you're lifting up on M2 with a force F1, which in essence will reduce the normal force on it and thus also reduce the friction on it. Okay, I gave you all these values. So first thing, like always, we want to draw free body diagrams. So this guy here is looking at the hanging box M1. We have M1G down. We have F2 to the right, pushing into the wall pushing back left with N1. We have friction going to go up, and we have T1 up. Now, how did I know friction was up? Well, look at the masses again. M1 is 50 kilograms. M2 is 20, M3 is 10. And that gives you a good idea that this box here is super big. Thus, it's going to make the whole system kind of accelerate to the left and down. Okay, so M3 is going to go up the ramp, M2 is going to go left, and M1 is going to go down. That's the direction of the acceleration. And there's a chance we were wrong, and the equations will tell us we're wrong, but that is the assumption we're going to make. Thus, I drew friction up on box 1. Okay, so now let's go over here to box 2. We have tension. T1 is pulling it left. T2 is pulling right. Friction is going to be to the right. F1 is up. The normal force of the table is up. And of course, M2G is down. And then we go over here. And we have the rope T2 pulling up the ramp on M3. We have M3G down, of course. We have friction down the ramp. And we have N3, the normal force on it, normal, which means perpendicular to the surface. So it is up and right. It is perpendicular to the ramp. Okay, we take these and then we algebraically write X and Y hat for each one of them. This is horizontally looking at this box. F2, the right forces minus the left forces. Then we have the down forces minus the up forces. And again, I picked down because I'm assuming that M1 is going to accelerate down. So for M1, I'm calling this positive. Then I look at the top box. I have T1 to the left, friction to the right, T2 to the right, and that equals MA. Remember, this down direction is the same as this left direction, which is the same as this up the ramp direction. You got to understand that this system, M1 is going to go down in the same way M2 is going to go left, which is the same thing that M3 is going to go up the ramp. Those three directions are the same, and that's the function of the pulley. Okay, so we write all of these, and this hanging one, because we're pushing it into the wall, it creates the normal force. But since there's a normal force, there's going to be friction. Same thing over here. This is a little weird one because I'm actually pulling up on box 2, right? That F1 pulling up, and if you can see, it's going to reduce the normal force. It's helping the normal force fight against gravity. And so the normal force, when I put it in for friction right here, it's going to be T1 minus friction, where friction is mu times the normal force, but the normal force is M2G minus F1. Again, think that through. F1 reduces the normal force, which will then reduce his friction. Over here, it's just the classic kind of box on the ramp. We have tension up, friction down, it's weight down. Again, I know I cut it off. I just kind of ran out of paper. So it's T2 minus FF minus M3G sine theta equals M3A. And then the Y hat, it's N3 minus M3G cosine theta equals 0. So if we replace the force of friction with mu n on each of these cases, we get this for box 1. That's the weight of box 1 minus the rope minus friction equals it. This is it for box 2. The rope pulling left, friction opposing it, the other rope pulling right, equaling it. And then over here, we got the rope pulling up, friction going down, and the weight component of M3 going down. Well, again, I would argue you have to be able to get to this equation, the one I now have boxed, without any of this stuff. You've got to be able to think it through. But if you need to, you have to be able to write them out. And so I'm going to take this one here and solve it for tension, which I did. This one here and solve it for T2. And then I'm going to chuck it in to this guy. And what happens when you do that, you end up with this system equation. And I would argue, like I have in class, that what I have boxed now You have to be able to get to that without the algebraic substitution. Run a thought experiment. Ask yourself, what forces are making this system accelerate in the direction we've decided? Well, the only one is m1g. It's the only thing making it move. What's all opposing this thing from moving in that direction? Well, we have this term here. This term is the friction on m1, and that's because F2 is pushing it into the wall. Now we have this term, which is the friction on the top box. Now, the top box, normally, it's just mu m2g, because the normal force is normally m2g when a box is just chilling there. But this box isn't just chilling there. F1 is pulling up on it, which reduces the normal force, which reduces friction. And so this is the frictional term for that top box. Then we have the weight component of m3 down the ramp, and then we have the frictional force on F3 also down the ramp. So weight is making it move of m1. Friction on m1, friction on the top box, gravity down the ramp on m3, and friction down. And this whole thing right here, that's the net force on the system, and that causes the system's mass to accelerate at a certain value. At this point, we can chuck everything in, and we can find the acceleration of 4.53. And then once we know the acceleration, we can come up here to that guy, and we can find T1, and then we can come over here to this guy and find T2. Okay, we actually can use this guy too if we wanted to. Once you found T1 using this guy over here, we could have used this middle one to find T2 if you didn't want to use this. But since we already had this solved for T2, it's just as easy, and you get these solutions. So practice this big force problem again. It makes you really think through all the different forces between tension and friction and normal force, things on ramps, things on flat tables, things hanging. But this is certainly a test-worthy type question.